It is the middle of October, which means that I should have had my candidacy exam done at this point. But that did not happen, and instead, I find myself less than, 24 hours, or not 24, 12 hours from my from my topology exam, which is early tomorrow morning. And yeah, it should be pretty clear that I'm pretty under the weather, pretty sick. I don't know who sneezed in my hamburger, but I'm pretty mad at them right now. But I'm a graduate student, so I'm not allowed to email my professor 24 minutes before the exam starts and say, hey, I can't do it. Can I wait a week and then do it then? You know, that's what my students do to me. But I've been preparing for this exam pretty thoroughly. I've been pretty much practicing every day for the last 3 weeks. So if all goes well tomorrow morning, I should be done in like less than 15 minutes. The way that he structured the exam is pretty convenient. You know, I'm thankful for the way he structured it, but the thing that has me worried is that of the list of theorems he gave us, 6 out of the 8 were really easy, and I have those down pretty pat. What am I trying to say? I know them very well. The other 2 theorems are the well-ordering principle, which takes like 6 pages to prove, and then the Tikhonov compactness theorem, which takes not as many pages, but still pretty long. I did not memorize any of those 2. I maybe looked over it once or twice long ago, but I don't remember how to prove it. I know you have to do something with chains, maximal and minimal chains, but the way that he's going to do the test is that he picks a random number, and then we pick a random number, and then we add them together, take modulo 8, and that number that we get is the theorem from the list of 8 that we end up proving on the exam. So as long as 7 or 8 doesn't show up, I'll get 100%. If 7 or 8 shows up, then I got to try harder next time to make up for lost points, because I don't think I'm going to have enough time to learn either of the 2 theorems tonight. Maybe one. I might do Tikhonov tonight, but both of them probably not going to happen. I don't feel well. I was going to learn a boat this weekend, but I've been kind of bedridden, not doing much. But the other points for the test come from the homework that he's given us, and we get to choose 2 out of the 8 homework problems he gives us, and the more challenging the homework problem, the more points it's worth. So I thought in this video, if you can stand listening to my voice, I was going to go through problem number 5 and then problem number 7, which are worth 5 and 7 points respectively. The theorem, by the way, is worth 5, so 5 plus 5 plus 7 gives you 17, which is more than enough for an A on the exam. So he does not give partial credit. So even if like everything's perfect, but you miss a line, you're not going to get any credit for it, which is the way it goes, I guess. I don't know if I'm going to teach tomorrow either. I might have my friend cover for me, just come home and sleep. Depends on how well I feel. Supposedly I'm going on a date Tuesday, which I really don't want to cancel that either, because you know how people are. As soon as there's any type of pushback, they're like, no, okay, never mind, I don't want to go with you anymore. But that's not appropriate for a math channel. What is appropriate is going through the solutions. Okay, so problem number 5 says that if you have a set E, it can be any set you want, subset of any topological space, and it can literally be any topological space. Then what is the most number of distinct sets one can make using the interior and closure operators? So I can take the interior of E, closure of E, interior of the closure of E, closure of the interior, and you can make this chain as long as you want. You can do interior, interior, closure, 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 interior of E. You get the idea. You can go absolutely bananas with the number of interior closure functions that you can use. So the proof is actually, the problem's not actually that hard. And my claim is that 7 is the maximum number you can get. And I've come up with an example that you can read here. But basically, we start with the set E, where E is the set of points 1 over n, where n is a natural number, union the interval from 2 to 3, where you poke holes at points 2 plus 1 over n, where n is a natural number. So this set is a countable disjoint union of open sets, because we remove 3 afterwards. And then we look at all rational numbers between 4 and 5, union the open interval from 6 to infinity. So this example is not one that's on the internet. The solution to this problem is on the internet, but the example that is given, you can find it on Wikipedia. Most people that did this problem with me, they used that example from the internet. I made this one up just by playing with it. The first example I came up with didn't work, and then I had to add this set that is in the center of the screen in order to make it to work. But if you take the interior, you know, you lose this set because it's all isolated points. This is open. You don't get anything from here either. There's no open intervals in there. And then that's an open set. So you get the union of these two, which give you this line. And then if you take the closure, you know, you're just throwing in all the limit points. I should have mentioned here that the topology I'm using is the standard Euclidean topology on the real number line. But it should have been clear from the context. Man, I don't sound very good, do I? If I laugh too hard, it starts to hurt and I'll start coughing, and then that'll be gross for the video. So I'm going to try and keep it monotone. But anyway, you throw in all the limit points, which you can verify there. But if you take the closure of the interior, so you're taking the closure of this set, which just gives you the interval from 2 to 3, and then from 6 to infinity. And if you take the interior of the closure, you're taking the interior of this set, which gives you those intervals, 2 to 3, 4 to 5, and 6 to infinity. And then if you take the interior closure of the interior, you know, at this point you're just removing and putting back in endpoints if you keep going. So if I take, if I take this set and I put closure here, then I'll get 2 and 3 and 6, but that will be the same as this set that I have up here. So the closure of the interior of the closure of the interior is just the same as the closure of the interior. And if I take the interior, man, that's horrible voice crack. But if I take the interior here, that's like taking the interior here. No, what am I saying? No, sorry. Interior here is the same as this set. So you kind of get this flip-flop back and forth. You're not picking up anything else. So we have 7 distinct sets here. And we need to verify that 7 is the maximum. And so I kind of alluded to it just now that if you do IC, so I'm using shorthand notation, I is interior, series closure. Those sets are the same, so I need to prove that. And I use a couple of properties. For example, I use the property that if I take the interior of any set, regardless of the topology and regardless of the set E tilde, the interior of the interior is the same as just one interior. And that should be clear, right? Because the interior is always open. And if you take the interior of an open set, it is the largest set contained within itself. So 1 should be clear. 2 is usually proven in some sort of textbook, but it's also pretty clear as well that if you take double closure, you don't pick up any more limit points. You still get closure. So this stuff we're allowed to use for free. I asked him about it. He said, yeah, you can use it. It's not that big a deal. Oh my gosh. The death of a struggling grad student on the channel. Ooh, okay. And then also, if you have A subset B, then the interior of A is contained in the interior of B, and the same deal with the closures. That one's also pretty obvious. So using those properties, I make the following two claims. The first claim is that ICIC of E tilde is equal to IC E tilde. So the first thing we do is we do left subset of right. So the first line basically just says the interior of a set is contained within that set. That's pretty clear. And then you take the closure of both sides. So now I'm invoking 2. And then double closure doesn't get you anything, so you just get closure. And then I invoke 1 and take the interior of both sides here to get this guy, which is exactly what I want to show. The next direction, let me straighten up the camera, is we notice that a set, so this thing is a set, is a subset of its closure. That's always true. And then if you take the interior of both sides, that's invoking 1, you get this. But double interior doesn't change anything, so you just get 1 interior. So IC is a subset of ICIC. So we have the first claim. Claim number 2 is now we've swapped the roles of CI, and it's also pretty easy. The interior of a set is contained within that set. Take the closure both sides. Double closure doesn't get you anything. So you have CIE tilde. So that's good. And then, for the next line, a set is contained within its closure. Take the interior of both sides. Double interior doesn't get you anything new. And then take the closure of both sides. So you have CI contained in CIE tilde. So you have both claims. So this problem's pretty short. I'm pretty sure it's correct. I did not check out the solution with the instructor, but I showed this solution to a friend, and then he checked it with the instructor, and he said that it was correct. So this is should be a guaranteed 5 points. Okay. I think I showed this problem on the channel maybe a week or 2 ago, but I did not have a solution written up. Okay, problem 7. Normally, when the instructor gives hard problems, they're so difficult that you can't even look them up on the internet or even solve them, because he has given us problems that are open. They're open problems and hasn't told us before. But this semester, for some reason, he's given us some problems that are much simpler. You know, the quote-unquote hard problems are much simpler. For example, this one, you know, that you can look up on the internet, or even, like, I think Wikipedia has it, maybe Stack Exchange. But the problem is that you have a topological space with unique limits. So it enjoys the uniqueness of limits property. In metric spaces, you know, metric spaces are pretty nice because, you know, all limits are unique, and it's kind of hard to come up with an example where it's not, you know, if you're just playing around with different topologies. But anyway, I'm rambling. If you have unique limits, then must X be a Hausdorff space? And the answer is no, and we're going to proceed by counterexample. Particularly, this is the co-countability, or the co-countable topology, whatever it's called, where we're going to denote X as the set of real numbers, and the topology tau is the set of all subsets such that the set is either empty or it has a countable complement. And the first thing that we have to do is to check to make sure that this is, in fact, hold on, I'm sitting on my foot, and my foot's falling asleep. we have to check to make sure that this is a topological space. And that's generally kind of easy to do. Well, let me be careful. Most of the time when I was in graduate school and I had to check to see if something's a topological space, all you have to do is check the three properties. So the first property is that the empty set and the whole set itself is in tau, and there's almost nothing to prove here. It's pretty straightforward because the empty set's countable and we forced it to be in there, in the beginning. The second property is that the space is closed under finite intersections. So if these finitely many E's are in the are in tau, we have two cases. The first case, if at least one of the sets EK is empty, then the intersection is going to be empty, and we force that to be in the topology, or force that to be in tau from the very beginning. If for every k, EK is not empty, then you just take the complement applied to Morgan's law, and then we get a finite union of countable sets, which is countable, so it's going to be in tau. Third property. I don't know how much, I was going to say, I don't know how much bass my voice has in this video, but to myself, I have a lot of bass, but then, my voice cracked there for a second, so I went straight to treble. So we have arbitrary union. If at least one of the E's is X, then the whole union is going to be X, which by number 1 is in tau, so we're good. If no EK is X, then the complement of the union is the intersection of complements, and each of those E alpha complements is contained in an E alpha complement. This set is smaller than this set. It's contained within it. And these guys are countable by assumption. And a subset of a countable set is countable. So we know that the union is in tau by definition. So the three properties are checked, and we have shown that X tau is a topological space. After about 17 minutes, my voice is really gone, man. My head doesn't really hurt though, but sleeping is a bitch. Man, you get up every hour to spit in the sink. Anyway, I'm sorry for being gross. But sometimes you get sick in graduate school. Claim limits are unique. So we let xn be a convergent sequence. We consider the set of all terms in the sequence that are not equal to the limit point x. This set is for sure countable because it's a sequence. It contains elements of a sequence. And under our co-countable topology, we know that fx is a closed set, which means its complement is open. And since x is in the complement of fx, we can say that it is an open neighborhood of x. And by definition of open neighborhood, we know that there exists an index n1 such that for every n bigger than n1, xn is in fx complement. But if it's in fx complement, by the definition of fx, we know that xn has to be equal to x. So that's what we get here. Now, suppose that xn converges to some element y. So this is kind of the way of showing something is unique. You look at a sequence that converges to 2 points and say, okay, those 2 points are actually the same. And then you have uniqueness of limits. There are other ways too. If you have a metric space, then maybe you can look at the distance between 2 points, but we don't have that here. We're in a weird topology. But if you repeat the exact same steps up here, down here, but this time with y, then really we get some new index n2. such that xn is in Fy complement, which means that if xn is in Fy complement, xn is equal to y. It's the same exact argument. And then we do undergrad real analysis. Let n be the maximum of those two indices. And then for any n bigger than big N, we know that xn is in the intersection of the two, because it's got to be in both at the same time, which means that xn is equal to x is equal to y. And that's true for every n bigger than big N. So any convergent sequence is eventually constant. You know, it reaches the limit point and it stays there forever. So you have uniqueness of limits. Almost died there. Okay, so if you made it this far, I don't know why. You should go watch Math Sorcerer at this point. Or Michael Penn. He probably does videos where he's actually healthy. I wish I was in as good a shape as Michael Penn. He's a model mathematician for health. Don't be like struggling grad student. It's not good. But we claim that X is not Hausdorff, and I'm going to proceed by contradiction, assume that it is. So what does Hausdorff mean? It means that for any two open sets, F1 and F2, such that their intersection is empty, so they're two disjoint sets, I can find open neighborhoods of F1 and F2 where the intersection of those two open neighborhoods is empty. So I really just wrote down what it means to be Hausdorff here. And now I'm going to take a closer look at these two open sets. Because they're open, we know that their complements are countable, which means that I can find a family of points, ui, for I in some indexing set, big I, that's countable, maybe empty. And same thing for Vj, where j is in J, countable, that I can write U1 as R, get rid of this set, U2 is R, get rid of this set. And then if you take the intersection of those two, it's really R, get rid of both of them, which is here. But this set is countable because it's a union of two countable sets. And R is uncountable, so if you remove a countable set from an uncountable set, it remains uncountable. Which means that this set is not empty. And that is where our contradiction comes from, because property 3 says that U1 and U2 are disjoint. But here it says they're not disjoint. So that's where our contradiction comes from. Oh my gosh. I guess I'll look over Tikhonov a little bit. Probably go to bed early. Oh, shoot, I got laundry. Oh, it's nothing but a struggle. But eventually you stop being sick and then you can do math. I may just do the test tomorrow morning and then come home and either cancel class, which I don't think I'm allowed to do, and just find someone else to cover it for me. Other than that, I'm not going to anything tomorrow. Except for that test. I don't want him to give me a retake and have him change the rules. I've been practicing too much for this test. Anyway, this was a mess of a video, so if you made it this far, I'll make you like a channel member or something. I don't know. Probably not. Thank you for watching.